So if you turn it'll get hot, and there'll be a temperature gradient. It'll be hotter. The fluid will be hotter at the bottom and cooler at the top.
Yes.
But if you heat it up, if you turn up the temperature a bit more, this fluid will start to move. The hot fluid, you might know, hot fluids are less dense than cold fluids. Right? They expand a bit, so the density goes down, so they have buoyancy. A bit of hot fluid wants to float on top of the cold fluid.
Mm-hmm.
But it starts out underneath the cold fluid.
Yes.
And it wants to get on top.
Yes.
Right, because it's buoyant, it's less dense. What they're talking about. Really.
Right.
So it's specialization. That's probably the same thing in biology and chemistry. And so everything has become so. There's so much science and so many scientists, and it's become such a big part of society that you're lucky if you can keep up with your particular niche.
Right. Now this is off the cuff, but are you familiar with string theory?
Not as a practitioner.
Okay.
I can tell you what I picked up about it by
Sure.
reading the opinions of other physicists, which is string theory is an artifact of the dearth of experimental evidence. So there was something called the Standard Model, which is our basic theory of elementary particles and interactions. That's our theory of matter. That was developed starting in, you could say, the 1950s, got going really, really hard in the 60s, and achieved its final form around the 70s. And the latest accomplishment in that theory was the prediction of the Higgs boson and its experimental discovery. So that's the most accurate and most successful theory in physics, because it predicts things to incredible accuracy, many decimal places. Right? But it arose as a way to understand experimental evidence. So we have this data from particle accelerators. How do we make sense of it? So the theory at every step, the theory is highly mathematical, highly theoretical. In fact, this book we'll talk about later.
Okay.
There's a lot about that. But it was constrained by experimental data. If you had an idea and you worked it out and it didn't agree with the data from the accelerator, either existing data or data that you could predict, you tried something else. The problem with, since that time, there's a limit to how much energy you can put in the collisions in an accelerator.
Yes.
Right? And so there's a limit to the energy of the collisions and the spectrum of particles that you can observe.
Yes.
So we reached that limit, but the theorists never stopped.
Yes.
So you still want to unify, for example, gravity with quantum mechanics, but there are many different ways you can think about doing that. The problem is these different ways of thinking about it are not constrained by experiment anymore, because we've reached the wall of available experimental data. So theorists are free to do all the beautiful math that they want without constraint. And unfortunately, string theory, the physicists who know more than I do about it, who criticize it, point out that it has no experimentally testable predictions and it never has. And either that or there are so many versions of string theory, all called string theory, that you can predict a whole wide variety of phenomena that disagree with each other, and you cannot decide which one is correct, because there's no experiment that you can do that constrains you to one or the other. So the short answer to your question is string theory is mathematics. It's no longer physics. It's simply mathematics, because it doesn't have contact with the empirical world.
Okay.
It doesn't have contact with anything we can observe. It's simply a mathematical game.
Okay, simply a mathematical game. All right, so your training. So we collaborated with the Friends of the Arlington Planetarium, but I didn't realize you had such an impressive academic pedigree. You have a BA in physics, mathematics and music from Hampshire College, and a PhD in physics from Dartmouth. Talk about your science training. Was it a smooth ride, or were there challenges along the way? And then say a few words about can you say a few words about your dissertation?
Well, I went to Hampshire College is a non-traditional college where you don't have traditional majors. So you're free to sort of mix things up a bit.
Mhm.
They have high academic standards, but you can be a little creative in how you design your program of study.
Mm-hmm.
So I was interested in pursuing physics in graduate school, but because I also, in undergraduate school, wanted to study a lot of math that physicists don't usually study, and also music. I studied music composition pretty intensively there. I was missing some courses because there wasn't just no time to do everything. So when I graduated with a degree and went to graduate school, I hadn't had every course that a typical physics major would have had. So my first year of graduate school was a struggle. I had to make up. I had to take extra courses and make up for lost time, but eventually I filled up the holes in education, and I survived there. It was a little rocky the first couple of years, making up for my missing background.
Okay.
And then while I was in graduate school, I didn't know what research problem I would go into.
Yes.
I just knew it's a nice department. They accepted me even though it was clear that I was missing some knowledge, some physics knowledge. I took a chance on it. And when I was there, after finishing my coursework and looking around for a research project, I talked to a professor who did fluid dynamics as his specialty, which is a branch of classical physics. The majority of people in that department did plasma physics and solid-state physics. But he alone did fluid dynamics. And I talked to him once, and he said, this is what I'm working on. And it seemed so interesting to me that there were I didn't know up until then that there were still active and exciting research programs that had direct contact with what you can see when you look out your window at the clouds, or when you see a river flowing by your house. Those things are still research problems. And I said, oh, if I can work on this is fascinating. So I decided to go with him and work with him and do research in fluid dynamics.
Okay, so I was going to ask you just briefly, like, what that is. You kind of alluded to it, but the quick explanation of fluid dynamics is that how fluids move throughout the Earth, their natural properties?
Even fluid dynamics is a vast area with specialties, and I can't even understand all papers in fluid dynamics. So there are fluid dynamicists who study the flow. Well, for example, theorize about the flow at the center of the Earth and how that creates a magnetic field. That's magnetized, electrically conducting fluid. There are others who study weather prediction, for example. That's part of fluid dynamics, meteorology. Because when we say, a lot of people, I should make this clear because people aren't aware that when physicists say fluid dynamics, they're talking about anything that flows, air, water, right? It's not just liquids.
Yes.
The difference between liquids and the atmosphere and gases, at low speeds, they obey the same equations.
Yes.
They flow in the same way. But at high speeds, the difference is that air can be compressed and it can have shock waves and sound waves. Well, liquids have sound waves too, but they don't affect the flow. But you can have an airplane, if it goes close to the speed of sound, suddenly you get a shock wave, compressional waves, and so then you have to have other terms in your equation. So that's the difference.
Okay.
Other than that, if you're dealing with speeds far away from the sound speed, it's the same physics.
Yeah, I was just thinking as you were saying that, and not to politicize this, but I've taken an interest in the climate debate. And I didn't realize how many physicists were involved in those experiments, and how many. I didn't realize how many physicists were involved. You would think that weather people, but yeah, if they have backgrounds in fluid dynamics, then they would be interested in weather patterns and precipitation and those kinds of things. So,
well, climate science is sort of an application of fluid dynamics, but it has other sciences built in.
Yes.
It's fluid dynamics with addition of radiation effects. So you have to have the radiation balance of the sun coming in and being absorbed. So there's a lot of material science, radiation transport, is what we call it, and geology and things like that. But the fundamental science behind it is fluid dynamics. It's like weather prediction, but on a long scale.
Yes.
Instead of next week, it's next decade.
Yes. Okay. Fluid dynamics. Okay, I have one more general science question, and then we'll I'm going to ask you about your career. But
I didn't answer your question about the dissertation.
Oh, that's right.
I don't want to cheat you. I don't want to.
Yeah, I'll watch the playback. Wait a minute, he didn't answer that question.
So, Even after deciding to work in fluid dynamics, it took almost 2 years to decide on a problem to solve.
Yes.
Because there's a lot to learn.
Yes.
I mean, the thing is, it's not a discipline that's really taught in the classroom much. It used to be. But in physics departments nowadays, usually there's no course in it. So people who go into it have to learn it themselves.
Yes.
There are a lot of classic textbooks and so on. It's based on classical mechanics, so you have the background, but then you have to learn what's built on top of it. Right? They used to teach things like elasticity and continuum motion and things, but it's not really taught much anymore in most departments. So I read the classic textbooks and a lot of papers, and I eventually settled on a problem. I became fascinated with what's called pattern formation in fluids. So everyone has seen, if you look at the clouds, you can see sometimes they form interesting patterns like stripes or a bunch of blobs in sort of a regular pattern. And that's the pattern formation based on fluid dynamics plus the release of energy in the atmosphere.
Mm-hmm.
Right? But the problem I solved was sort of similar to a cloud pattern problem, but idealized. So imagine you have a tray of water, just like a square baking dish filled with a thin layer of water, and imagine you can heat it, you put it on your stove, but your stove is perfect, so it heats it very uniformly from the bottom,
Mm-hmm.
right, instead of having a spiral. So imagine that the tray is very thick, so it distributes the heat perfectly. So if you turn it, it'll get hot, and there'll be a temperature gradient. It'll be hotter, the fluid will be hotter at the bottom and cooler at the top.
Yes.
But if you heat it up, if you turn up the temperature a bit more, this fluid will start to move. The hot fluid, you might know, hot fluids are less dense than cold fluids. Right? They expand a bit, so the density goes down, so they have buoyancy. A bit of hot fluid wants to float on top of the cold fluid.
Mm-hmm.
But it starts out underneath the cold fluid.
Yes.
And it wants to get on top.
Yes.
Right? Because it's buoyant, it's less dense. So how does it get from the bottom to the top? It doesn't just, the whole fluid doesn't simply turn over as a unit. What happens is some of the hot buoyant fluid from the bottom bubbles up to the top and trades places with the cold fluid, which then gets heated because now it's at the bottom.
Mm-hmm.
So it keeps turning over. Right? The hot fluid comes up, cools down, sinks down, the cold fluid goes up, and so it's like it keeps moving.
Yes.
Right? But this occurs in a pattern of motion over the whole surface.
Yes.
So this pattern of motion can be stripes, that we call convection rolls, or it can be an array of hexagons or an array of squares. It can form different geometrical patterns. So it's an old problem in fluid dynamics to predict what those patterns are. Right? Should it be hexagons? Should it be circles? Should it be squares? I mean, the fluid has to move somehow. It has to decide on a pattern. And the fascinating thing is that the equations that describe how the fluid moves don't have those patterns in the equations. So somehow there's a balance of forces, a balance of equilibrium, where this pattern emerges more or less spontaneously.
Yes.
In the motion. And this has been studied intensively since early in the last century, but it's still a topic of research. So my problem was to figure out, to calculate how you could make the fluid, how you could force the fluid to move with a particular pattern that you wanted it to move in. What you have to do. How if you put an irregular pattern of heating on the bottom, how much irregularity you would have to have before you could overcome the fluid's natural tendency to flow one way and make it flow another way. So for me, it was just an interesting mathematical and physical problem, but it has applications for understanding clouds and understanding convection systems in the Earth.
Okay, so understanding where the fluid is moving based upon energy you're putting in to the system. Okay. Okay. So, thank you for watching this discussion. It will be continued in subsequent installments. Please leave any questions or comments in the comments section below. And finally, please like, share, and subscribe, especially if you are new.